Can you hear? Yeah. Oh, that picture is very old. I got to update it. So the original title of this talk was The Last 12 Years of React Performance. And to start, actually, I'm curious, who here has already used in personal projects or in production React 19? Quite a few hands. What about React 18? More hands. Who has used React 17? OK. 16? Fewer hands. 0.13? Yay! I think that was my first version. 0.2? I do not believe it because that version was not public. The first public version was actually 0.3 in May 2013. So React has been around for 12 years. Over these 12 years, it went through a ton of changes. Some of them improved composability, some of them directly aimed to improve performance. But today, I want to talk about the improvements that most developers didn't notice, that I didn't notice for years. Improvements that React slipped under our noses to make our apps faster. In other words, I want to talk about the invisible hand of React performance. And to start, let's talk about useEffect. So who here uses useEffect? Who loves useEffect? 3 hands, yeah. Well, of course, but I'm going to show you one reason why useEffect is actually a pretty good hook. So useEffect is a hook that lets us synchronize things, right? We can run some logic when the component mounts, or when some props change, or on every change. Before useEffect was introduced, the same thing was achievable with lifecycle methods. You would have a class component, and a component that's written as a class, not as a function. And that class would have a render method that returns the JSX. And methods like componentDidMount or componentDidUpdate, which would also allow me to do something when something updates, just like useEffect, but with more lines of code. So when React 16.8 came out, useEffect pretty much replaced componentDidMount because it was just so much easier to use. And that was a great change, but alongside that big noticeable usability change came a much more hidden but very intentional performance change, which I'd like to talk with you about. And to talk about it, I have a quiz. So I have this React component. When the component renders, it sets the background document body background color to red. When it mounts, it sets the background color to blue. Question: which colors will the browser render? Option A, red, then blue. Option B, blue, then red. Option C, only blue. And option D, only red. Take a moment to think. OK, so who thinks it's A? A few hands, yeah. Who thinks it's B? A few other hands. Who thinks it's C? Also several hands. Who thinks it's D? OK, that's quite a lot of hands. So the right answer here is C. But now I have this code. This is the same code, same component, but instead of componentDidMount, it uses useEffect. My question is still the same. Which colors will the browser render? Take another moment to think. Who thinks it's A? OK, I can see a few hands. Who thinks it's B? Also a few different hands. Who thinks it's C? Just 2 or 3 hands. Who thinks it's D? Also several hands. So the right answer here is A, red, then blue. So with useEffect, the right answer is A, red, then blue. But with componentDidMount, the right answer is only blue. This difference, does anybody know why there's a difference, by the way? Someone says, OK, I see one hand. Great. You can skip this part of the talk. The difference is a result of a very intentional performance decision that drove useEffect design and helped to fix a whole class of performance issues. But to understand the difference and to understand the issues it fixed, we need to take a detour into how browsers render things under the hood. So the browser's rendering pipeline is complex, but we need to know only two things about it. The first thing is whenever a browser has to render an update, like maybe you clicked something, maybe a timer fired, whatever, the browser always goes through 4 stages. First, it runs JavaScript. Then, if the JavaScript has updated the page, the browser recalculates the style and recalculates the layout of the page. And once that's done, the browser paints the result on the screen. 4 stages whenever there's any update to the page happening. That's the first thing that we need to know. The second thing that we need to know is that browsers use a lot of caching. Every time the layout updates, every time any update completes, the browser caches the layout and remembers it until it needs to update the next time. So if you render the app, for example, for the first time, and the browser calculates that the header is 200 pixels tall, the browser will remember that and keep that in memory until you, for example, click the header and the header expands, and the browser recalculates the layout and now remembers that the header is 500 pixels tall. Oops, not clicking, clicking. So when you have, for example, a button ref in React, which is just a reference to the DOM node, right? And some JavaScript code tries to read the height of the button, the browser would not compute it at the moment when you're calling this code. The browser, no. The browser would just go to cache and read the value from cache, which is very quick. Now, oh yeah, arrows that demonstrate that. Now imagine what happens if the button, which height we are reading, was just mounted. What happens if it's not yet in the cache? What would the cache return then? Or how would the browser behave then? This is not a quiz, but take a second to think what would happen. What do you think would happen? What would happen is the browser will be forced to calculate the styles and the layout ahead of time. The moment you try reading them, the moment you read the height, the browser will freeze the JavaScript, compute the styles, compute the layout, and then unfreeze the JavaScript and return the height back to JavaScript. This works, but this is a performance issue that's called a forced layout calculation. And this was a pretty common problem with componentDidMount. Take a look at this code. Say you have a class component. It's a button component. It renders a button, and then it checks if the button is taller than 300 pixels. And if yes, then it does something with that button. And this code uses componentDidMount. In React, componentDidMount runs right after render within the same block of JavaScript. So if componentDidMount needs to read from the layout, like it does here, and this layout isn't cached, and it isn't because we just mounted the button, right? There was no previous update with this button being already in the document. What would happen is the browser will have to do a forced layout calculation, which will freeze componentDidMount until it completes. This is a common issue, and this is a common enough issue that you see even dev tools warning about it. If you ever did a performance recording of some kind, you might have seen these violet highlights. This is the forced layout recalculation. This is what happens when you read from the layout when the caches are not there yet. So compare this to the component which uses useEffect. Unlike with componentDidMount, useEffect runs not in the same frame, but in the beginning of the next frame. And this changes everything performance-wise. Now, if I render a button first, React would render it, then the browser would compute the style and the layout, and then it would paint the result on the screen. And then only once all this is over, useEffect would run and would try to read from the layout. And so now when it does that, when it runs and when it reads from the layout would already be cached, right? Because the browser computes the layout here, and the browser puts the values into the cache here, in the end of the frame. So no forced layout would happen anymore. useEffect would simply read from the cache, and that would return instantly. And so if you check DevTools, you won't see any violet rectangle warnings anymore. You wouldn't see any forced recalculations. You would only see JavaScript, style, layout, paint, and then in the next frame, a little more JavaScript. Now, notice how none of the reasons why useEffect was introduced and why everyone switched to useEffect were about performance. When React 16.8 came out, the reason to migrate to useEffect was just because it provided a simpler, easier to use API. But when we moved to this new API, this issue, this whole class of issues, the forced layout recalculations, they disappeared. This is the example of the invisible hand of React performance. This is how React made our apps faster without us even realizing that. And that's the first example. Let's talk about the next thing, batching. And for that, I have another quiz. So this button has an onClick. The onClick calls this event handler, and the event handler has 4 setState calls. It calls setIsLoading true, it flips setIsPublic from true to false or false to true, it calls some APIs, it receives some value from the APIs, then it calls setState for the 3rd time to set the value received from the APIs, and it calls setState for the 4th time, setIsLoading false. So 4 setState calls. setIsLoading, setIsPublic, setPublishThat, setIsLoading again. The question is, how many renders will this onClick cause? Option A, 3. Option B, 4 in React 17 and lower, 3 in React 18 and newer. Option C, 3 in React 17 and lower, 2 in React 18 and newer. Option D, 4 in React 17 and lower, 2 in React 18 and newer. Again, take a moment to think. Sorry, this is very loud through the microphone. Okay, so who thinks it's A? Wow, I see no hands. Who thinks it's B? 1 hand, 2 hands. Who thinks it's C? A few hands. Who thinks it's D? A lot of hands. So the answer is C. This is happening thanks to update batching, which is one of the earliest invisible React performance optimizations. It was introduced all the way back in version 0.4.0 in 2013. It changed a bit over the last 12 years. It received the biggest overhaul in React 18. And it's another invisible hand that makes our apps faster without us realizing that. Let's talk a bit about how batching works. So batching is when you have several setState calls, but they result in a single render. The newer versions of React, React 18 and React 19, have only 2 renders because setState calls 1 and 2 and 3 and 4 are batched together. But in React 17, only setState calls 1 and 2 are batched together. 3 and 4 aren't. Raise your hand if you know why. Yay. OK, so to understand why, let's talk about how React is implementing batching. So let's say I was Meta, and I was implementing React from scratch. What would be the simplest way I can implement the setState call? The simplest way is probably something like this. Whenever someone calls setState, I take that state and I perform the update right away. That's also how React was working in the very first releases before batching was introduced, with different function names, of course. You would call setState 3 times in a row, and React would render 3 times in a row. Now, React 0.4 introduced batching. The subsequent versions improved it a bit, fixing some edge cases, and so in subsequent versions of React, up until React 17, setState actually started looking a bit more complicated. Here's how it looked in React 17. First, whenever you would call setState, React wouldn't process the update right away anymore. Instead, it would have a global queue of updates, and it would simply push the update into the queue. Second, after queuing the update, React would check if it's batching updates right now. If it's not, if batch updates is set to false, then setState would process the update right away. But if if batch updates is set to true, then no processing would happen. setState would only push the update into the queue and do nothing else. Batch updates, by the way, is just a simple global flag that various parts of React can set to true or false. Now, if you're batching, and if batch updates is true and setState isn't processing the update, then what is processing the update? Their answer is the part that has set, the part of the code that has set batch updates to true is responsible for that, is responsible for processing the update. Specifically, this part is the event listener. Here's how this works. When you pass some callback into onClick, and that click actually fires, the following happens. First, React sets the batch updates flag to true. Second, it fires the callback, it fires your actual onClick or whatever event listener. Third, it sets the flag back to false. And fourth, now that it's done handling the click, any updates that were scheduled are finally processed. This is how batching works in the older versions of React, 17, 16, 15. And that's why when you have this code in React 17 and below, only the first 2 setState calls are batched, because the first 2 setState calls are inside an event listener, which follows this line of code. But by the moment you call await, the original callback, this very callback, it finishes executing. So React flips the batch updates flag back to false, and then whenever this code finally fires, the batch updates flag is already false. There's nothing that sets it to true. So these 2 setStates are calling 2 separate renders. That's why you have 3 renders in total in React 17 and below. Now, how does React 18 avoid this issue? How does React 18 batch updates that happen after await, if they are not wrapped with anything, if there's no code that can set the global flag to true or to false and to process the pending updates? How does it do that? The trick looks as follows. First, starting with React 18, the global batch updates flag is no more. All updates are now batched by default. The event listener wrapper, now that there's no flag, simply calls your callback directly on click or whatever it is. Second, the process update queue function, this one, is still called, but in a very specific manner. Whenever you call setState, React executes promise.resolve.then process update queue. What this achieves is this runs process update queue, but not immediately, but rather at the end of the frame after all existing JavaScript. And finally, React ensures that it only calls process update queue once. If you call setState more than once, then process update queue will still be scheduled only once. And so here's what this does. You should remember this chart from a little earlier. This is how it works. You have a frame, and the frame starts running onClick. The onClick calls setState 3 times, and every setState pushes into the queue. The first setState also schedules the process update queue function. then this first unstate completes, and then the second unstate completes, and then the third unstate set state completes, and then the whole onClick completes, and then maybe some other JavaScript runs. And then finally, only after that, only after onClick and all other JavaScript finishes, the scheduled performance update queue function finally kicks in and processes the queue that was collected during all these set state calls. This is how, in the newer versions of React, set state 3 and 4 are batched. You call set state 3, it pushes into the queue, it schedules processing, but it does not process anything right away. Then you call set state 4, it also pushes the update into the queue, and then JavaScript completes and process update queue kicks in, and both updates are processed together. I should have probably had a slide to demonstrate all that. Well, you saw it, but like for these specific words. Anyway, this is update batching, and this is another invisible hand of React that makes our apps faster out of the box. Let's talk about, thank you. Let's talk about one more thing, which is Suspense. And guess what? I have another quiz. So here, I have a bit of JSX. It's a header component with a few children. There's an icon, a menu that's collapsed by default, and a button that opens the menu. Now, imagine that this is a server-rendered app. If this is a server-rendered app, there will be a few moments when the app won't work as expected. For example, if you just open the page and no JavaScript has loaded yet, then if you can click the button, but the button wouldn't do anything yet, right? Because there's still no JavaScript. And if JavaScript has been loaded, but the app is still being hydrated, well, this is my question to you. What happens to the page if the button is clicked while the page is still being hydrated? Option A, nothing happens, the click is ignored. Option B, nothing happens, a warning is logged. Option C, the click is remembered and is replayed once hydration completes. Option D, the page freezes. Take a second to think. Who thinks it's A? I see a few hands. Who thinks it's B? I also see a few hands. Who thinks it's C? That's quite a lot of hands. Who thinks it's D? I see one hand. The right answer is D. The page freezes. Hydration, by default, freezes the page for as long as it takes to hydrate the app. So when JavaScript loads, if the app has 10,000 components, the page will be frozen until React hydrates all 10,000 components. If you click the button during hydration, then the page would already be frozen, so the page would freeze, the user would feel the page frozen. The page would freeze. Okay, this did have a bit of a twist. Okay, but here's another quiz. Let's say here's the same app. Let's say I have the same app, same question, but this time the insides of header are wrapped with Suspense. What would happen to the page then? Again, the same for options. A, nothing, the click is ignored. B, nothing, the warning is logged. C, the click is remembered and is replayed. And D, the page freezes. Same app, but now it has Suspense. Who thinks it's A? I can see a couple of hands. Who thinks it's B? I can see no hands. Who thinks it's C? That's quite a lot of hands. Who thinks it's D? One hand. The answer is still D. The page will freeze again. But this time it will freeze for a much shorter period of time, only to hydrate the elements inside the Suspense. By the way, everybody who answered C, you could have been right, because React experimented with C early in React 18 development cycle, but they were not able to make this implementation successful, so nothing in React currently actually does C. Instead, they opted to do D. But the page will freeze, but the page will freeze for a much shorter period of time. Instead of here's how this works. Suspense generally is a component that's used for data fetching, right? The idea is that you wrap some parts of your page with Suspense, and then when you're fetching something from inside that part, Suspense will render the fallback. However, that's only one part of the idea behind the Suspense. A much less noticeable part of the idea is that Suspense also introduces something called selective hydration. The idea is described in a discussion in React 18 working group, and I go into it in depth in my another talk. But the gist is as follows. As your site or app grows, more and more parts of it are going to get wrapped with Suspense to do data fetching. Like maybe if you're the Airbnb website, then you'll have the search wrapped with Suspense, and then each listing wrapped with Suspense, and so on. And so what React does without Suspense is when the page hydrates, React freezes the whole page. It starts hydrating the logo, then it hydrates the header, then it hydrates the search, then it hydrates the listings, and the page stays frozen until every element on the page is hydrated. If you click something, you'll have to wait until the whole hydration is complete. But with Suspense, React behavior changes. React will now hydrate the app Suspense by Suspense. It will hydrate, first it will hydrate everything outside of Suspenses. And then it will hydrate one Suspense, make it interactive, switch to the next Suspense, make it interactive, switch to the next Suspense, also hydrate it, make it interactive, and so on. And so if you click any of these Suspenses while the page is being hydrated, like for example this one, React will finish hydrating whatever Suspense boundary it's hydrating right now. And then React will prioritize hydrating this specific thing that you clicked. It will switch to that specific Suspense boundary. And it will hydrate that specific Suspense boundary. And the page would still freeze. But it will freeze only for the duration that it takes to hydrate this Suspense boundary. Even if the other boundaries aren't hydrated yet, it would only hydrate this one and then give the control back to the browser. And this will be much faster. This will be much shorter. This is selective hydration. I'm not going to get into how that works under the hood. Again, that's a whole separate talk. But this is yet another example for React shipping invisible performance improvements under our noses without anyone noticing. So useEffect, batching, Suspense, all those are examples of React's invisible hand that made our apps faster, often without us even noticing that. There are quite a few more examples that I wanted to talk about, some successful, some not. Sadly, they didn't fit in. And I know React gets quite a lot of burn, sometimes deserved, but this invisible hand is something I honestly really, really like. So.